Hi and welcome back. In today's tutorial we will talk about linear classifiers. So what exactly are linear classifiers? Well, the main goal of a linear classifier is to classify data into labels based on a linear combination of input features. Therefore, these classifiers separate data using a line or a plane, and they can only be used to classify data that is linearly separable. Before we start, here I have imported the necessary libraries including PyTorch, matplotlib, numpy and some libraries like torch vision and a function called transforms. We will start by creating a toy dataset on which we will train our linear classifier so we get a better understanding of how the linear classifier works. So we will define x1, x2 and y. x1 will be a numpy array that has the values 1, -1, -1. x2 will be also a numpy array, but we will change up the values, so 1, 1 and -1. And we will also set the data type for both to be numpy floats. So copy this up here. And now y will be a numpy array, and we will have three classes, so 0, 1 and 2. In order to train our linear classifier, we need more data than this. So we will just create some dummy data like x1 np.repeat. So this will repeat this sequence of numbers. So we will pass in x1 and we will repeat it for 100 times. We will copy it here, just change up so it's x2, and also do this for the y variable. Currently we have 300 numbers that are this sequence, and this one, and in order for them to not overlap we need to add some noise. So we will add noise to the variable x1 and x2. So x1 plus equals to np.random.rand. We will add 300 numbers or the len of x1 and we will multiply it with some small number, for example this one. I will copy this and paste it on here and just change it so it's x2. And now we need to shuffle our data, so I will create a index shuffle that will be np.arrange from 0 to the len of x1, so this will have 300 numbers. And then I will shuffle this index, so np.random.shuffle, and I will pass in index shuffle. I will run this. And now that our data is shuffled, we will now apply it to x1, x2 and the y variable. So x1 will pass in index shuffle. I will copy this. x2 index shuffle and also y with the index shuffle. To understand the data, we will now use a scatter plot to scatter the points. So we will plt.scatter. We will pass in x1 and x2, and for the color we will set it to be y, so depending on the class. And this is our dataset, so we can see that we have three classes and that they are linearly separable. And now we need to transform our data into tensors, so we will simply do x1 torch will be equal to torch.fromNumpy, pass in x1, we will do the same for x2 and the same for y. And now we need to reshape our data. So to reshape a tensor, we will use the function .view and we will pass in -1 and 1. We will do the same for the two other variables, like this. As we did earlier, we will split our data so we have training and testing data. So in order to do this, we need to create one big X, which will be torch.horizontally stack. We will place x1 torch and x2 torch in here. I will run this piece of code. And down here I will create xtrain, xtest, ytrain and ytest. So for the xtrain I will take the x and I will take, for example, the first 250 numbers. For xtest we will take the 50 numbers that are left. And ytrain will be y, first 250, and also for ytest we will take the last 50 numbers. And now we can simply check the shape of xtrain. we can see that it is a tensor of 215 numbers and it has two features in it. Now that we have a better understanding of how the data looks, we can start creating our classifier. So we'll create a class, linear classifier, and in here we'll pass in torch.nn.module. First we'll create a init function, so def init. It will accept two parameters. It will accept a input dimension and a output dimension. For the input dimension we will set it to be 2, because we have x1 and x2, and for the output we will set it to be 3, because we have 3 classes. Now in this function we'll call super linear classifier, and we'll pass in self and call the init. We'll create a self.linear, which will be a torch.nn.linear, and for the input we will set to be the input dimension and output dimension for the output. And then we'll create a forward function that will accept x as input, and it will simply return the self.linear, and we apply it on x. We can now call the model linear classifier. We will set the default values for the input and output dimension, and we will create a criterion. So it will be torch.nn.cross-entropy loss. Earlier we used the binary cross-entropy because we had 2 classes. Now that we have 3 classes, we will be using the cross-entropy loss. For the optimizer, we will be using torch.optim.stochastic gradient descent. We will optimize the model.parameters, and the learning rate will be 0.01. Before we start training the model, we will create a list, all loss, in which we will store the losses. We will train our model, for example, 1000 times, so for epoch in range of 1000. We do the forward pass, so output is equal to model on xtrain. Let's train it not for 1000 but for 10,000 iterations. As usual, after the forward pass we will calculate the loss, so loss will be criterion of the output and y train. We need to reshape it so it's flattened, so we'll pass in -1. Then we will append to this list all loss.item. After this we will do the backward propagation, so loss.backward. After we obtain the loss, we will now optimize the parameters, so optimizer.step, and 0 to gradients, so optimizer.0grad. And we will simply train the model. After our model finished training, we can now do a small test, so model.forward, and we pass in a tensor, for example 1 and 1. So we know that this should belong to the purple class, or class 0, that is this class over here. So now if we run this, we can see that the highest number is this one, so it belongs to class 0. And now we can plot the loss, plt.plot all loss. And by looking at this plot, we can see that our model's loss was dropping here until it reached somewhere near 0. After this, we can now simply access the values for the weight and the bias by taking the model.parameters, and I will print out the weight. So we can see that we have a 3x2 matrix. This is the weight for the 0 class, this is for the first class and the second class. Now, in order to use the weight and the bias, we will now convert it to be numpy arrays, so we will simply do the weight.detach and .numpy. And we will do the same for the bias, like this. Now, how can we use this weight and the bias? Well, if we look at this image up here, we can see that we can draw some lines here that can separate these points. So we will use the weight and the bias for that. So I will define 2 variables, x1 fit and also x2 fit, to be a numpy linspaces, like this, linspace, from -1 to 1 and 100 numbers. And I will copy this, paste it down here, and run this piece of code. Then we can create the y1 fit, so it's the first line using the weight at 0 index, so we will use minus x1 fit multiplied with the weight at 0, 0, minus the bias at 0, and we will divide it with the weight at 0, 1. Then we can simply copy this, paste it 2 more times, change it so it's y1, y2 and y3. And here we will simply change it so it's the weight at 1, weight 2, bias 1, bias 2, and here also 1 and 2. Now that we have the data, we can now do a scatter of the points from above, and we'll set the color to be Y. So we will obtain a scatter plot as we did above, and then we can just draw the lines. So plt.plot x1 fit, y1 fit, copy and paste this 2 more times, change it so it's y2 and y3. And we need to set the axis to be equal. And one other trick that we need to do is, for example, we'll use the function plt.quiver, and we will set the center to be at array 0, 0, 0, and another one at 0, 0, and 0, not 1, 0, and the points will be the weight 0th index and the weight 1st index. Okay, so we get a graph that looks something like this, and the score here represents a 3D function depending on the features x1 and x2. And because of that, the score is a plane, so this plane here is a plane z equals 0. And we also have a plane that represents the yellow class, for example, the yellow score. And this line intersects plane z equals 0 at the green line here. Also, this arrow here represents that the score is increasing or it is positive here in this direction, and on the other side it is negative. So this simply means that these lines here represent an intersection of two planes. And these arrows show us where they have a positive and where a negative score for a particular plane. But because this is a very simple problem, we won't have any difficulties here. But when we look at this part here, we can see that we don't have any information what is happening here, when the blue line and the green lines are positive. So because of that, we will now create a mesh grid. So we will define x1 fit and x2 fit again. x1 fit will be a np lin space from -3 to 3 and with 20 numbers, and I will do the same for x2, -3 to 3 and 20. To be able to create the mesh grid, we will call mesh grid np.mesh grid, and inside of here we will pass x1 fit and x2 fit. By running this piece of code here, we will create our mesh grid, and I will simply just plt.scatter mesh grid 0 and mesh grid 1. And here we get our mesh grid. So now we need to convert the data, and we can do this the following way. X will be a np.hstack. We will use the mesh grid at 0th index, and we need to reshape it so it's -1, 1. And for the second value, mesh grid at the point index 1, also reshape it so it's -1 and 1. And then we will convert it so it's x.sType np.float 32, and we'll simply transform it so it's a tensor. So xtorch will be equal to x, or my mistake, torch.from numpy, and we will pass in x. Now if we check out the shape, so we print out xtorch.shape, we will get the following. We have 400 numbers and 2 features. Now you may be wondering, how can we pass these points? Well, as we did before, we will just use yPrediction, we will use model.forward and just pass in xtorch. Now, as we mentioned earlier, if we now print out yPrediction.shape, we will see that we have 400 vectors that have 3 numbers in them, so each representing a probability that it belongs to a certain class. So we need to get the maximum value from these 3 numbers. We can do this the following way. So yPrediction will be equal to torch.argmax, and we will simply pass in yPrediction, and the axis will be 1. And now if we check out the shape, so yPrediction.shape, we can see that we only have 400 numbers. And if we print out yPrediction, we can see that it is either belongs to class 2, class 0 or class 1. And by looking at this scatter plot here, we can see that our model classified these points over here to belong to class 0, these points over here to belong to class 1, and these points down here to belong to class 2. And also we can see that it separated these points by drawing some lines like this. Now that we have seen how the linear classifier classified this data here, we will now use a bit more complex dataset like the MNIST dataset. So we will start off by creating two variables, train set and test set, and we will call torch vision.datasets.mnist, and I will copy and paste it down here. And for the training set, we will pass in a few parameters like the root, where we want our dataset to be stored, and I will pass in data. Also, I will specify the download to be true. Then this is the training set, so train equals to true. And the same parameters, I will copy and paste them down here and just change the train to be false. Now, in order to train our model on this dataset, we need to convert it so they are tensors. So I will here specify a variable called transform and call transforms.compose. And inside of these brackets, I will specify all the transformations that I want to apply to my data. So I will call transforms.toTensor to convert my data to tensors, and also transforms.normalize to normalize my data. And inside here, for the parameters, we need to specify the mean and std of the dataset. You can calculate this, or you can find the data online. So I will pass in 0.307. And also for the std, the value is 0.3081. And now run this. And here, just specify transform equals to transform. And the same down here. And run it. Now that our dataset is downloaded, we can now move on and create our loaders. So I'll create a train loader and test loader. For the train loader, I will call torch.utils.data.dataLoader, and I will do the same for the testing. Paste it down here, and in the brackets here, I will specify the training set. I will specify also the batch size, so I want that to be 4. Also, we will specify shuffle to be true and number of workers to 2. And all of this will be the same down here, just change it so it's test set. And run it. After this, we will now create an array called classes, and we will specify how many classes we have. So we will create a np range from 0 to 10 with a step of 1. Now, what did we exactly do in these lines? Well, we first downloaded the dataset using these commands here. Then we created a transform variable which contains all the transformations that we want to apply to our dataset, and we pass it in here as this parameter. Then we created a data loader to load our data in this variable, and created a object or a NumPy array classes that contains number from 0 to 10. Now we may be wondering, how can we access now these images? Well, we will simply create a data iter variable, and we will call iter on the train loader, for example. And then to extract the images, we will do images and labels equals to data iter.next. And now, because our data is in batches, we have 4 images in one batch, I created this function imShow, so it unnormalizes the images, it transforms it into NumPy arrays, and transposes that image. Then we will just simply here call imShow, and we will use the torch vision function .utils.makeGrid to make a grid of these images, and we just pass in the images. And we can see that we get these 4 numbers. And also we can now print out the labels, so print labels, and we should get 7, 3, 8 and 0. The next step would be creating our model, but we already defined it in the previous example, so we will now just call it linear classifier, and just change the input and output dimension. So the input dimension will be the shape of the image, so it's 28 by 28, and the output will be 10 because we have 10 classes. We will also define the criterion. It will be torch.nn.cross-entropy loss, and for the optimizer we will use torch.optim.stochastic gradient descent. We will optimize the model parameters, and the learning rate we will set it, for example, to be 0.001. Now we can train our model. So we will define a list all loss. We will train our model, for example, 10 iterations. So for epoch in range of 10, we will now create another for loop for images and labels in train loader. Because we are working with batches and we will iterate through each batch. And we will create another list for the temporary losses after each batch. Then we will do the forward propagation, so output will be model, and we pass in the images, and we need to reshape them. So there will be images.shape 0 and -1. After the forward propagation, we will calculate the loss. So loss will be criterion, and we pass in the output and the true labels. Then we do the backward propagation, so loss.backward, and we can now optimize our model parameters. So we will call optimizer.step, and we will also zero the gradients. So optimizer.zeroGrad. After the loss is calculated, we will now append to the temporary loss the loss.item. After all the batches are done, we can then append to the all loss, and we will append the mean from all the batch losses, so temporary loss. And we will just simply print out after each epoch. We will print out the epoch. We will also print out the loss. And just train. Now, if we look at these numbers here, after the model is finished training, we can see that the loss was dropping. But for better visualization, we will just plot it out, so plot all loss. And here we can see that the loss was dropping. And it would drop even more if we pump up the number of iterations. After this, we will now test the accuracy of how good our linear classifier classifies data. So we'll create two variables, correct and total, and we will assign them to be 0 and 0. And because we are now testing our model, we will now turn off the gradients with torch.noGrad, and we will iterate through our test loader. So for images and labels in test loader, we will do the forward propagation. So output will be, we will use the model on images.view, we will reshape them, so it's images.shape of 0 and -1. After this, we will extract the maximum value, so we will do predicted, and we will call torch.max on the output.data and pass in 1 here. After this, we will now append to the total number of images in this batch, so we will add labels.size of 0, and the number of correct, how many correct predictions our model had. So predicted equals to the labels dot sum and dot item. And after this finishes compiling, we can now calculate it. So we will take 100, multiply it with the number of correct, divided with the total. And our accuracy is 92.24. Another way that we can test the accuracy of our model is by testing for each class individually. So we'll create two lists, class correct and class total. Then we will create it as a list 0 for I in range of 10, and do the same for the class total, so list 0 for I in range of 10. Like this. Then we will turn off the gradient calculation with torch.noGrad, iterate through all the batches, so for images labels in test loader, we will now do the forward propagation. So output will be equal to our model on the images dot view and images dot shape of 0 and -1, so it's flattened. And now I can copy and paste this code from here to take out the maximum value. And after this, we will now calculate how many correct our model got. So C will be predicted equals to labels dot squeeze. Now, because we have 4 images in one batch, we will now iterate through each one of them. So for I in range of 4, we will extract the labels. So label will be labels of I, and then we will append to class correct of that label. We will add C of I dot item. Then we will add to the total of that label 1 and just run it. After this finishes compiling, we can now create a for loop I in range of 10. We will iterate through all of those classes and we will print out the accuracy of, and this is classes of I, and then it will be 100 times the class correct of I divided with class total of I, and just run it. And by looking at these numbers here, we can see that the highest accuracy has the number 0 and 1. One interesting thing that we can do now is see how our linear classifier interprets the data or the images. To do this, we will now extract the weight and the bias of our models, so model.parameters. We can now create a for loop for I and data in enumerate of the weight, and I will create a plt.figure fixed size 20 and 17, and down here we will now create a subplot plt.subplot 5 and I plus 1. Then after this we will just do plt.imshow the data.detach.reshape, so we'll reshape it so it needs to be 28 by 28. And then we'll just turn off the axis. And now, if we look at these numbers here, this is the visual interpretation of how our model sees the data. So this is a number 0 here, number 1, 2, this is a 9, and so on. Let's take a look at this example here. Let's imagine we have 3 classes, and these images here represent one sample from each of those classes. If we input these into our linear classifier, it will give us a score. So, in this example, we will see what will happen if we change one pixel from black to white. How will it affect our score? We will change its value from 0 to 255, but because it is scaled, we will take the values from the minimum to the maximum. We extract the weight and the bias here, and these are the weights visualized for each of those classes. And let's see how the output changes by changing the pixel from the minimum to the maximum. When I change it, it can either lower or increase the score. And because we work with linear classifiers, the score will be a line. So this graph here represents the scores. And looking at the graph here, we can see that transitioning from black to white, the 0 class score dropped. The 0 class is the blue line here, meaning that the score was bigger when the pixel was black, in this region here. The opposite is happening here for the 1 class, the orange line. It got a better score when it was a white pixel here. So, one additional example will be seeing what will happen if we change 2 pixels. Well, this here is the score, and it is the same as before, just here we don't have a line, we have planes. In this corner here, the pixels are dark, and in this corner here they're bright. So this means that the 0 class has a better score when the pixels are darker, and the opposite for the 1 class, it has a better score when the pixels are brighter. For the 8 class here, it is not really clear. It is showing that the score is bigger when this pixel here is brighter, and this one is darker, meaning that if this pixel here is white, and this pixel here is dark, it will give a higher score. And that would be it for this tutorial. If you found this video helpful and you learned something new, drop a like and subscribe to our channel for more videos like this one. I will leave a link down in the description of our blog post where you can read more about linear classifiers. Thank you for watching and be safe.